Hello, my name is Alexis Segoviano and I am in Group 1. My team members are Anaí Ramos, Priscila Rodriguez, April Todd, and Eileen Moriel, and I will be presenting Lab Report 8. So for Lab Report 8, we focused on Faraday's law of induction, and in this experiment, my group and I investigated how changing magnetic field can induce a voltage or EMF and a coil. This experiment allowed us to confirm and explore Faraday's law by comparing how different magnets and coil setups affect the induced voltage. For Lab 8, we observed Faraday's law and measured the voltage of a wire that is changed in response to the magnetic field. Faraday's law is practiced when an individual turns on the heat of an induction stovetop. Our prediction was if we increase the magnitude of the magnetic field by 20%, the induced voltage would also increase. And we based this on Faraday's law due to a greater change in magnetism should create a higher EMF. In simple terms, the faster or stronger the change in magnetic field, the larger the voltage that will be produced. Our goal was to test this relationship by using different magnets and coils and see how changing variables can affect the voltage. The materials we used for this experiment were three magnets, one being circular, another one being rectangular, and another in a cylinder shape. We also used four coils, but we mainly used the 200 and 400 turn coils, as well as a voltage sensor and passport interference, a Pascal magnetic field sensor, and a stand with a clamp, a cushion box, wires, and a measuring stick. We set up the coil vertically with the cushion box below to catch the magnet and connected both the voltage and magnetic field sensors to capstone. The voltage versus time graph was set to a record at 100 Hz sample rate. For the procedure, for step 1, capstone was set up and the Pascal magnetic field sensor was connected to the passport interference. Next, the digits was set up to read the values of each of the magnets and capsule. Next, the magnetic field strength was set up to 1x and the unit was set to read millitelson or MT. For step 4, the circular magnet was at the base and the rectangular magnet was sample 2 and the cylinder was sample 1. Each of the three magnets were brought within a range of the magnetic field sensor and the values were inputted into table 1. Lastly, for step 6, to find the percent difference, the values of the base was subtracted from the value of each of the samples, then divided by the base value and multiplied by 100. Next, for table 2, the passport interference and Pascal voltage sensor were used to find the voltage V. For step 8, a graph was set up in which X was the time and Y was the voltage. The 200 coil was used to find the voltage for each of the three magnets. The coil was then attached to the stand and the box was placed below to catch the magnet. A ruler was used to make sure the magnet was dropped from the same distance each trial. For step 11, to find the percent difference, the value of the base was subtracted from the value of each of the samples, then divided by the base value and multiplied by 100. Lastly, for the final part, we chose sample 1 to try and increase the voltage by changing the coil to 400. Our data and analysis could see in the video that we are running the magnetic field sensor over each of the magnet,
Sí.
and for the circular,
Me salió un
which we
número high,
chose
and then I
as
was
our
trying to
base,
stuff it right at the luego que le puse seguía negative. Yes, yes. You can leave it negative or you can do it positive. It doesn't matter.
that we chose as our base,
Anything on chair.
gave us the value 14.4013 MT.
I saw you go to
And for
Nate.
the cylinder magnet,
Ajá, pero es que se la
it gave
pega
us a
al
value of
Yeah, I
negative
let me record it, like, stay
3.6792 MT. And for the rectangular magnet, the sensor gave us negative
Sí,
0.8955
porque
MT.
estaba raro. Sí, me salió un número high, and then I was trying to stuff it right at the
So we found the percent
Yes. You can
difference
leave it negative or you can do it positive. It doesn't matter. Pero ahorita, a ver, anything on chair.
by dividing the base minus sample over base times 100. And for sample 1, it gave us a
I saw you go to
74%
Nate.
difference, and sample
Ajá, pero es
2,
que
a
se la pega al
93%
Yeah,
difference.
I let
For the
me
percent
record it,
change,
like,
we divided the increase over the decrease. And in the video, you could see us doing that for each of the magnets and getting the values from the
Sí,
sensor.
porque estaba raro. Sí, me salió un número high, and then I was trying to stuff it right at the luego que le puse seguía negative. Yes, yes.
As
You
well
can
as
leave it
setting it
negative or
to
you can do it
0 each
positive. It
time a
doesn't matter.
magnet was run
Pero ahorita, a
over.
ver, anything on chair. I saw you go to Nate.
As for table 2, you could see us um, dropping each of the different magnets through the coil, and table shows the measured amplitude of each of the spike. On this part of the experiment, the base was also kept the same. It was a circular magnet, and as well for the other magnets, sample 1 was a cylinder and sample 2 was a rectangle, and each of them were dropped from the same height. The first video shows us dropping the base 5 times through the coil of 200. The second video on the right shows us dropping the cylinder, and the bottom is us dropping the rectangular magnet. And the values maximum and average EMF are the values that we obtained from the graph peaks. From sample 1, we see that there's a 57% difference, and for sample 2, a 66% difference. And we concluded that the stronger magnets probably produce higher induced voltages. And here are the values that we obtained, the peaks for filling in table 2. In the final part of the experiment, we tried to increase the induced voltage by 20%, but without changing the magnetic field strength. Our ETA helped us calculate that our goal that we were trying to reach was going to be 0.084 V. And for our first trial, we did try the coil 1600 and believed that we did get our goal number, but turns out that we were wrong, and we kept on testing out each different coil until we saw a value close to our goal number. And in each trial, we kept the same height. And we noticed that from in 400, we achieved a peak of EMF of negative zero point zero 0.08 V, which was closely reached our target. And you can see in the videos, we did test out each of the different coil boxes and dropped the magnet in an average 5 times through. We changed the number of coils turns to increase the induced voltage by 20%. We chose this variable because Faraday's law predicts that the more turns creates a higher EMF. So using the 400 turn coil gave us negative zero point zero 0.08, which was very close to 0.084 B goal and showing higher accuracy. We ignored the negative because the negative is just showing us the direction. The percent differences in the magnitude field, which were 74 and 93, were greater than those of the EMF, which were 57 and 66, but both changed in the same direction. The ratios were similar as an average from 1.3 through 1.4, meaning that the changes were proportional within a small margin. These results did predict support our prediction, and since a stronger magnetic field and more coils turns both increase the indulge voltage. The lab showed us how controlling one variable, like the coil turns, affects EMF and helps us visualize Faraday's law in action. In conclusion, we verified Faraday's law of induction, showing that the induced EMF depends on the rate of magnetic flux change and the number of coil turns. Attempts to increase EMF by strengthening the magnet were ineffective, producing only just a small rise in voltage. However, when doubling the coil from 200 to 400 resulted in a 22.7% increase in EMF and exceeding the 20% goal. This demonstrates that adjusting the number of turns is a reliable and predictable way to enhance or increase induced voltage, making it more effective method for optimizing induction systems. These results did support our prediction since both a stronger magnetic field and greater number of coil turns increased the induced voltage. The experiment also helped us realize how controlling one variable, such as the number of turns, provides a reliable and linear method for adjusting the EMF. Overall, the lab did successfully demonstrate Faraday's law induction in action, and it showed us how well the rate of magnetic flux change can be difficult to control in the setups. The coil properties, especially the number of turns, offers a predictable way to optimize induced voltage. As for the credits, I did the procedure materials, I did the voiceover, and also participated in the math during the experiment. Priscilla did the data and analysis, Eileen did the conclusion, and April did the introduction. Thank you.